So let's look at some more properties of Laplace transforms that will help us do some transforming of some more involved problems. So this one's going to be translation along the s-axis. This theorem says if we happen to have Laplace of a function f of t, and we're going to call it big F of s, then the Laplace transform of e to the at times f of t. So we've got this e to the at term in front of here is equal to the Laplace of f of t, where s is going to become s minus a. So we're going to translate, instead of having s in there, we're going to translate that to s minus a, and we're going to get an f of s minus a. So basically you're just substituting in, but really what it does is it shifts you along that axis, just a translation along the axis. The inverse Laplace of f of s minus a is the inverse Laplace of f of s, capital F of s, where s was moved from s to s minus a. Anytime you see that where you've got an s minus a instead of just an s in there, it'll be the same Laplace transform of inverse Laplace of f of s, but then you have an e to the at attached to it. So let's try a problem with this. Let's find the Laplace transform of e to the negative 7t times t to the 10th. So if we go look at our Laplace transforms, we see we have t to the n, and that translated as n factorial over s to the n plus 1. So that being the case, we know that this is going to be going to equal 10 factorial, because it's n factorial over s to the 10 plus 1 or 11. But it's not just s anymore. Because of this e to the minus 7t in there, there's actually more to this that's going to happen. And the more that this is going to happen is that instead of being just s to the 11th, it's going to be something else to the 11th. And as this theorem says, is instead of just being s, it's going to be s minus whatever the a is here. So it's going to be s minus whatever's up there. Negative 7 happens to be up there, so it's going to be s minus negative 7. So it's going to be s plus 7. So there's your Laplace transform of that. Let's try another one. The Laplace transform of e to the negative 3t cosine of 6t. So again, looking at our Laplace transforms, cosine of kt is s over s squared plus k squared. So instead of erasing, I'm going to think about it as I'm going to be replacing the s for something else. So it really is something over something squared plus k squared. And the k is the number inside of the cosine. So it's going to be 6 squared, what we're going to put in there. In this case, instead of just being s, that goes in here, because of this translation, we're going to translate this with s minus whatever happens to be the a up here in the e. It is e to the at, so since there's a minus 3, it's going to be s plus a negative 3. I'm sorry, s minus a negative 3, which is s plus 3. This one also would be s minus a negative 3, so it would be s plus 3. So we end up with, this one translates as s plus 3 over top of s plus 3 squared plus 36. Now, these translations with e to power a to the t next to it is very, very important. So you're going to find out in a lot of your Laplace transforms, they're actually already there. So if you look down here in your list, you're going to see there actually is an e to the at cosine of kt, and it tells you what it equals. There also happens to be a t to the n e to the at, and it tells you how it translates. So these have become very important, are very useful to us. So they usually are on your Laplace transform table. Now let's try the other way. Let's try undoing one. So I'd like to find the inverse Laplace of 4s plus 6 over s plus 7 squared. Well, unfortunately, this is not as nice and neat as we would like it to be. The thing is that, first off, we need to make it to where we don't have the 4s plus 6 over s minus 7 squared. We need to make that into something else. So we need to first do partial fraction decomposition. So if we do that partial fraction decomposition first, this becomes, well, we're gonna have to do this. So we take out our calculator and we're gonna go ahead and do the partial fraction decomposition of this. And when we do that partial fraction decomposition of this, this becomes 4 over s minus 7 plus 34 over s minus 7 squared. So using technology, you find out what that is. And then we can separate this up, and this is 4 times the inverse Laplace of 1 over s minus 7 plus 34, the inverse Laplace of 1 over s minus 7 squared. And so again, we want to undo this. So anytime you have an s minus something in the bottom, instead of just an s, you've got an s plus or minus something, you know that you're going to have a inverse, you're going to have that e power in there. So 1 over s is what we want to look for on our table. So again, if I go to my table, 1 over s always translates as just 1. So we know we're going to get 1 times e to the at, where in this case, the a is a 7. Sorry. The a is a 7 because it's s minus a that we're doing. So you can have 4 e to the 7t times 1 plus 34. Now again, we're looking for s minus 7 squared in our table. S minus 7 squared will get me t. So again, because we got the s minus 7, you will end up with an e to the 7t times t. Again, these are so useful. If you go to your table, you're going to actually find, if you look through that table closer, you do actually see a 1 over s minus a is e to the at. And you do, in fact, see a 1 over s minus a squared, and that's t e to the at. So you can actually see these are actually there for you in most cases, but I want to make sure you understand how they came about. So let's find the inverse Laplace of 2s plus 5 over s squared plus 6s plus 34. So as a reminder, you need to do partial fraction decomposition, but when you go to do partial fraction decomposition on this one, it's just going to give you back what you started with. So that tells me that we probably need to do completing the square in the bottom. So let's go ahead and do complete the square in the bottom. So when I do complete the square in the bottom, because I want this to be s squared, s minus something squared, and so forth. So I'm going to try to do the complete the square for this and see what we end up with. And so remind you that complete the square means you take the coefficient of the s term. In this case, it's 6. You divide it in 2, so you get 3, and then you square it, and that's what you add. But now I've just changed the problem. So I need to subtract 9, so I don't actually change the problem in any way. So I get 2s plus 5 over top of s squared plus 6s plus 9 is now a perfect square that factors as s plus 3 quantity squared. 34 minus 9, of course, is 25. So now we have what this would look like in this other form. The next thing I need to do is try to think about completing this partial fraction decomposition with this, but you want to keep your denominator the way it is, but you do want to do partial fraction decomposition at this point to find out what these are. Actually, we don't need to do that. I'm sorry. We just want to separate them up. So it'd be 2s over s plus 3 squared plus 25 plus the inverse Laplace of 5 over s plus 3 squared plus 25. All right, cool. But here's where the problem comes into play, is that I actually do need, if this is an s plus 3 down here, I need this s to also be an s plus 3. So I need to make that into an s plus 3. So I need to figure out what that would look like to make that happen. So I want to think of this as going to be 2 times s plus 3 that I want to have on the top. So now ask yourself, what did I really just add to this? Because then I can subtract it off. So I really want to know, what did I really just add to this to do this? So what I really added was, I have 2s plus 6, so I really added 6. So that means I need to subtract 6. So that I didn't change the problem. All right, so I've done that. So now what I can do is, again, separate these out and put this minus 6 over this denominator and combine it with this other one. So I now have the inverse Laplace of 2 times s plus 3 over top of s plus 3 squared plus 25. So that's my first one. I'm then going to have this minus 6 plus 5. Well, minus 6 plus 5, of course, is just negative 1. Okay. So now I can go ahead and find out what the inverse Laplace is. So now, again, I'm going to go look to see if I have anything of this form. And so I go looking through my, my table. So here's my table. And I'm going to look for where I have an s plus 3 over s plus 3 squared plus k squared. And again, you can either remember that anytime you have that s plus 3, it's going to be the same as the cosine. Here you got s over s squared plus k squared. That is the cosine. And then you know you're going to get that e to the kt. So this one here shows you get that e to the at in there. So we know from this, we can either use number 19 in this table or use the fact of what the inverse Laplace is of cosine and then add that e to the at on it. So this one is e to the minus 3t because we subtract, it's s minus a, so a must be a negative 3. So e to the negative at cosine of, this is k squared, so k must be 5, so 5t. Then we have minus, now let's see for this one, going back again to our table. In our table, 1 over s minus a, sorry, 1 k over s squared plus k squared is the sign. Oops, here's sign. K over s squared plus k squared is the sign of kt. So again, because I've got that s minus a, I know I'm going to have an e put onto it. But now I got to figure out what this is. So k must be, k squared is whatever number is being added there. We do need a k in the numerator. So going back to this, I know that I've got a k squared of 25. So that must mean k is 5. So I need to put a 5 up here. But again, that means I just changed the problem. So I need to do a 1/5 out here to get rid of that. So I now know that this is going to be 1/5 e to the minus 3t sine of 5t. Because this whole part gets me the sine, and that s plus 3 tells me the e to the minus 3t. Okay. Now we're going to talk about the unit step function. The unit step function is really important in what we're doing and will be useful in what we're going to be getting into. And it allows us to actually take piecewise functions and write them in a continuous format. So the unit step function, or known as the Heaviside function, is u of t minus a is equal to the step function of, well, it's a step, but it's also a piecewise function of 0 when 0 is less than or equal to t is less than a, or 1 when t is bigger than or equal to a. This function looks like, if I were to draw this, So this is your t-axis. Here's 1. So from 0 to a, let's say a is here. From 0 to a, when t is from 0 to a, you're going to be 0. So from here to a, you are the number 0. Once you get to a, you're going to suddenly jump up here to the number 1. And then we go from here on. So this is what the heaven side function looks like. Suppose we want to actually have f of t equal t squared to turn on 0, 1, and we want it to turn off on 0 to 1, and we want to turn on everywhere else. So graphically, what this is saying, you want to think of this graphically, is that from 0 to 1, we want this to be 0. So we want this to actually be like this until we get to 1, just a horizontal line at 0. After that, we want it to look like 1 squared. But we know what 1 squared looks, or t squared, sorry, t squared looks like is it's a parabola. And we know that when 1 squared is 1. So we know we're going to be that value there. And we know it's going to be a parabola from there on out. So it's going to look something like that. So we're going to have a parabola from 1 on, but 0 before that. And what we want to do is we want to write this instead of being a piecewise function. And this piecewise function would be 0 when we're 0 between 0 and 1, and t squared when t is bigger than or equal to 1. So this is what this function would look like as a piecewise function. But I want to write it as a single function using the heaven side function. And the way we do that is we actually think about what the heaven side function does, and then what this is, and realize that it's just a multiple. Because remember, the heaven side function is just 0 from 0 to 1, and then 1 from here on out. So that being the case, it means that it's just a multiple. T squared times 1 is just t squared. So it's just a multiple of that. So all we have to do to find out what this function is take t squared and multiply it by that unit step function. And it's t minus 1 because a is our stopping point where we change, and we're changing at the number 1. So it'd be t minus 1. All right, let's try another one. Let's say we have a graph now. We want to actually write this in the heaven side notation. We want to write what this function is. Again, we can write this as a piecewise function. It would be the number 3 when we're between 0 and 1. And then we're the number 2 when we're between 1 and 2. And then we're the number 1 when we're greater than 2. So this is what it would look like. And what we want to do is try to rewrite this in a heaven side notation. So we want to try to get this to kind of come out and get into a different notation using this heaven side function. So the first thing I notice is it's turned on at the beginning. So at the beginning, this whole function is equal to 3. So we can call it 3 at the very, very beginning. And it'll be 3 forever if we don't do anything else to it. But now at the number 1, we want it to be 3 to go away and 2 to come on. Well, you can't just say, I'm going to make 3 go away and 2 to come on. I'm going to think about, well, 3 minus what is 2? Well, 3 minus 1. So if I actually subtracted off 1 unit step function, t minus 1, because we're changing at 1. So it's going to be t minus 1 instead of t minus something else. This now at 1, this value will be 1, and 3 minus 1 is now 2. So it all works. Now let's see what happens. We're going to keep moving along. And at 2, we suddenly want to be the number 1, which means we need to, again, get rid of 1. So we're again going to subtract off 1. But this is going to be t minus, instead of being 1, we're now changing over at 2. So it's going to be t minus 2. Up before 2, this one is 0. So we haven't changed anything. Up before 1, this one's 0. Up before 2, this one's 0. So these two are both 0 at the start. That's why it's 3. Now at time t equals 1, remember this is your t-axis. At t equals 1, this one now turns on. So it's gonna be 3 minus 1, which gives me 2. At t minus 2, at time 2, this one now turns on, and we got 3 minus the one that was already on. That one stayed on. That one didn't change. So it's going to be 3 minus 1 is 2, minus another one is 1. In general, we can do this with any function. G of t, h of t. If we're saying we have a piecewise function g of t when 0 is less than or equal to t is less than a, and h of t when t is bigger than a, then we can think of it as g of t turns on at the start. G of t then we want to have turn off at a, so we're going to have g of t times u t minus a. That means it will now be 0 before, now it's 1, so g of t minus g of t, of course, is 0, it goes away. And then we want to add on h of t, which gives me, and we're going to turn it on at t minus a. So this one, basically it turns off g of t and turns on h of t. This is your normal notation that we use. So let's just try that for this one. We've got the piecewise function sine of 3t when 0 is less than or equal to t is less than pi. Cosine of 2t when pi is less than or equal to t is less than 2 pi. And 0 when t is bigger than or equal to 2 pi. We're going to write this in as a unit step function. So we're going to start at the beginning as sine of 3t. We need to turn that on at the start. So this turns it on because it's there. Now we want to turn it off at pi. So we're going to subtract off sine of 3t times the unit step function t minus pi. Remember, this is 0 before pi.